Good morning, everyone. Welcome back to this workshop. Will be the same procedure for this session as yesterday. We will have presentations, and if there is enough time, you have the time to ask questions. We have also the possibility again for the online audience to write questions into the Slido, and we would read that. Please don't forget to fill out the sticky notes that will be posted over there for the breakout sessions later. So, I'm Carmen Emmel. I'm from the German Meteorological Service, and I will chair this first session, which is Advances in Observations for Validation and ISSR Forecasting. Yesterday, we heard quite a bit about, for example, uncertainties, and the need of observations. If you have to do a prediction or a forecast, you need to know what's the current status, what's the current situation. And that's one reason why we need observations, to do a good forecast and reduce the uncertainty on that. You also need observations for validation. And we will hear about these different aspects today. Now I will first give you a short presentation about what we are doing at WMO, the World Meteorological Organization. At the World Meteorological Organization, WMO, is an agency of the United Nations, and within the organization we have a number of expert teams with members from the weather services, but also from industry. It's the hydrometeorological environmental industry. And one of these expert teams is the expert team on aircraft-based observations. We get data from the aircraft, usually temperature and wind, and if it's available, also humidity, and we hope to get more and more turbulence data as well. And there are different types. Maybe you have already heard about some of them. AMDAR is the classical that exists in the past. Some airlines know that term at least. Then there are others that come from the air traffic control, like Mode S and different ADS, ADS-B, ADS-C type data. And we are starting to work more and more with UAVs as well. And within this group, I'm the vice chair of the expert team on aircraft-based observations. And within this expert team, I lead the subgroup on water vapor measurements. And one of the very important topics of aircraft-based observations, especially in the context of water vapor measurements, is contrail avoidance. Our members in the team are, again, from the Met services and also from industry. We also have some invited experts that don't come from these very specific groups. And at the moment, our members are running 2 water vapor operational programs where we get the data in real time, and this data is shared with all the weather services worldwide. We have a European program with 9 aircraft that have a WVSS2 sensor. That's the only commercially available sensor at the moment on board. They are all on Lufthansa aircraft, and it's quite a limited program with just 9 aircraft equipped. In North America, there are about 135 aircraft equipped, and but also the area is a little bit larger. Still, Europe, if you compare Europe to the US, it's a NOAA program, so a USA program. The area is not that different in size. What do we work on? We wrote, for example, business case guidance for NMHSs, so that means weather services. We wrote a flyer on aircraft-based humidity measurements, what are the benefits, what is this data used for. We organized a workshop 2.5 years ago on this, with some people from this crowd were also there. We contributed also to a publication that IATA wrote on contrails, and several of our members are involved in contrail avoidance projects. And very important for us is the exchange with the stakeholders in industry. So now it's important that we work on expansions, and there's an expansion plan over the UK. It's actually happening right now. The first aircraft should be equipped with another sensor soon. And we are discussing with Nellie if we should write together a publication to explain clearer to the aviation industry why it's so important to have these water vapor measurements, and we need to find solution for data sparse areas. So that's from my side. To the first talk will be given by Nicolas from WMO, developing a water vapor sensor suitable for contrail avoidance, challenges and roadblocks.
Thank you very much. Thank you, Carmen. Thank you, IATA and Russian Aeronautical Society for this invitation. So, ladies and gentlemen, today I am going to propose to you to talk about different issues related with the aircraft-based observations programs. One is related to the technical aspects of the sensors, regulatory aspects, communications, funding, which is a big issue, and also I'm going to bring you some insights from the global aviation stakeholders on AVO meeting. So, first of all, related to the water vapor sensors, I brought this nice image, picture from Tim Rams with the Boeing company. We had this discussion about the different sensors. As you see, we have needs and we have non-sensors. Related to needs, we put all the focus in the past related all the sensors for assimilation just for numerical evaluation purposes and climate models. And also there is some efforts related to the stratospheric chemistry and radiative forcing, but related to upper tropospheric cirrus and contrails, this remains a challenge. So what we want to find and develop is just to ask the industry to develop a low-cost sensor in this range. We have the current existing water vapor spectral sensor number 2, which is already installed in the US and Europe, and also Carmen explaining the AVO program. And also there is some efforts from NASA to develop a specific sensor achieving these needs. And also we have a lot of research sensors around the world. The problem is we need to have a sensor, low cost, small sized, lightweight, reliable, and also self-calibrated. And the most important thing, to measure from 10 ppm to 25,000 ppm. So related with that, we need to take into account the external aerodynamics and sampling, the inlet design, the boundary layer interference with the airframe, in order to avoid all the contamination of different hydrometeorological species. And also, we need to take into account the structural integration barriers, I mean the fuselage penetration, hose, thermal management, and also autonomous operations of the sensors, and also one important thing, the cost and maintenance. This is important because we need to balance the high certification cost with the airline return of the investments. So, what are the regulatory challenges? First of all, is the supplementary type certificate. A high-resolution water vapor sensor require these specific certificates because this is not a part of the original aircraft design. Another topic is related to the agency compliance. I mean the Civil Aviation Agency's resource. They need to meet the standard of the Federal Aviation Administration and IASA, and also to meet the environmental qualifications, RTCA document 160 standards. And also, we need to meet an additional requirements such as instruction for continuing airworthiness. So this is another important topic, which in the research side is not well discussed. It's about the communications. We need to take into account that there are different ways to transmit data through air-ground communications. One is the well-known ACARS-based conventional systems, such as AMDAR, that use the flight management computer, CME, ATSU, depend of the aircrafts, using the standard RX620. Then we have another, which is electronic flight bag, which is an alternative solution using the current existing broadband in the aircraft or using another SATCOMs. This electronic flight bag needs to be connected to the aircraft interface device and connected to the flight management computer. Then we have ADS, Automated Dependent Surveillance. We have BEC, and also we can ask using the secondary surveillance radar mode S, but it's important to enable in the transponder the meteorological routine air report. Only 5% of the aircrafts around the world is activated, so we require from WMO and the expert in aircraft observation to enable this standard. This allows us to receive meteorological information real time. So another important topic is the data should be distributed free and unrestricted into the WMO integrated system. As you know, the global centers and NWP are connected to WIS and also the Met service. We need to receive this data in real time and also free and unrestricted. Another topic is the setup cost, installation cost. We need, obviously, for the sensor, installation cost itself, and also to put money in the regulatory costs, such as the ECTC, and also IT technologies for data processing. And also we have operational expenditures. I need to run communications, quality control of the message, and also to improve the data simulations in the numerical weather prediction centers, and also post-data processing for contrails avoidance management. WM members can achieve that, especially the two middle, I mean the quality control of the message and also data simulation in the NWP centers. So it's important to have a public-private participation to get a suitable funding mechanism for this. Finally, I brought here some takeaways from the Global Aviation Stakeholder Meeting on EBO, which was held last September. We discussed different topics, but most of the outcomes are related to the accelerated water vapor sensing, just to work with the standardized sensor specifications, and also we agreed to enhance NWP models to support contrail management, and also work close with the ICAO framework. This is important that WMO also signed a MOU with IATA, and we are working on that in order to support all the needs, especially in this in contrail avoidance monitoring. So collaboration for the civil aviation agencies, I mean ICAO, AINA aviation service providers, CANSO, IATA and Airlines, W1 Met Service, research entities, standardization organizations such as RTCA and Eurocare, DCPs, and also another key third-party stakeholders are critical. So let's work together to support this. Thank you.
Thank you, Nicolas. Do we have a question in the room? Yes, one question over there.
Thank you for the talk. I'm wondering how you begin to value the benefit of additional water vapor sensors when, particularly for contrails, they don't exist at large scale. So how do you kind of put a value onto the benefit that would bring to weather forecasts?
Yes, if you are talking about the contrails, you are measuring water vapor also for general purposes. But it's important to remark that contrails is only one part of the whole WMO system. But I just to I would like to remark that Contrail is also can support the general society. Because as you know, for example, all the Met services are engaged with the United Nations Early Warning for All. We are working on to provide special products for other communities, especially in Africa and South America. And also you are contributing with the social aspects. So this is one thing. Related with the benefit itself of getting these water vapor sensors is also to improve the image of the company. You are going to get better forecasting products, not only for contrail avoidance, also for field management. You are going to reduce the carbon footprint, and also it's important to provide essential information for research proposals, especially for global climate models. As you know, we have a lot of uncertainties. This uncertainty could be reduced with these sensors.
So this isn't a loaded question, it's just a query. There's a great deal of cost attached to climate mitigation for the airlines, upfront costs, implementing models into their flight planning systems, or indeed the hardware on the aircraft. So if they're providing data, there must be a cost, and that cost must be borne. Is it possible that the amount of money that might be due to the airlines for providing this data could go some way or all the way to offsetting those costs that they're going to incur as a result of trying to carry out these contrail mitigation operations?
Yes, but it's a challenge question. Very good question. One thing is that we don't have exactly the numbers of the airlines. The business case should be done by the airline itself and also with IATA. So this is something that we can provide. We are just supporting Met service in our. I'm representing the Met service and also with Carmen. So specifically financial numbers, we don't know exactly the numbers behind of the airlines, but we can provide all the technical information to achieve that.
I missed one of the online questions for the previous talk, and it's how do you value the benefit of new water vapor sensors? One way might be to do data deny experience, but this relies on there already being some data, and that fits very well to the next talk actually. So please listen in to the next talk and you will get some answers to this. Marius, maybe you can also mention shortly the OSSEs that are possible. Just say a sentence about it. This would answer it. So next one up is Dr. Marius Neumann from DWD, and also Dr. Björn Beckmann. He's online, so he will be switched on at the end of the talk and present the last part.
Thank you, Carmen. So I'm going to talk on how DWD is testing the capabilities of currently available on-route humidity observations done by sensors, WVSS2 sensors in the EU and in the US. Huh? Yeah, okay. So in general, how do we do a forecast at DWD? Well, we need a model and we need observations, and we somehow need to combine those. In the process of combining the observations and the model, we call data assimilation. And this left side of this slide is going to be some kind of outline for this talk. So first I'm going to talk about how to get observations, and then I'm going to tell you how those assimilate into our currently available models. So in the case of contrails, what specifics do we have to keep in mind when we try to make a forecast? Well, if we want to find contrail regions, we need to find ISSR. And ISSR are ice supersaturated regions. So to find those, we need to forecast the humidity in those, in all of the regions. And forecasting the humidity is quite of a challenge. Because relative humidity is quite a challenging parameter itself. It's a combined parameter out of different actual parameters. And the NVP models have to deal with supersaturation in the case of ISSR, which requires specific models or specific microphysics in those models. But on the other side, we need quite accurate predictions of those regions to justify any reroutings. To do that, well, we need an NVP model which features supersaturation. We have that now. It's the icon model with a two-moment scheme. So the remaining bottleneck is the availability of humidity observations. Those are quite rare. So we have a project going in the EU where there are 9 aircraft equipped with WVSS2 sensors and are submitting observations also en route. And a similar data set is available in the US, where we have a quite larger amount of sensors available. So the question now is, what can we do with those currently available data or observations which we get? And is this sensor working as a quick fix to enable good forecasts? And if it does, then how many of those do we actually need to get the forecasts we need? So let me show you the sensor a bit. So this is an A321, and down there you see an inlet, which was retrofitted to this. And if you are this guy looking down that hatch over there, then you can see the actual sensor. This is the inlet in larger, and the actual sensor is this. It's this shoebox-sized thing, and it sits in the inside, and those hoses connected to the inlet down there. And those are the sensors running in the EU. This is one of the EU sensors. And if you look at which data it's producing on, well, a single flight basis, then you see something like this. So in blue, you see the altitude, so you guys can get an estimate for the phase of flight it's currently in. And in green, you have the relative humidity over ice shown. So you can see that this flight entered a high humidity region at first, even got into the supersaturation regime a bit, and then it exited that region and got into a dry space. And I want to point out a specific point over there, because in that case we got lucky, because at that point, position and time, someone was actually there and submitted us a picture of the sky at that moment. And you can see that there where we measured some oversaturation, we actually see in ISSR. Okay, but to actually show you the entire data set, this is the current status in the EU. So green are ascents, blue is en route, and white are descents. And those are the 9 sensors currently available. As you can see, this data is not that evenly distributed. This airline is clearly based in Frankfurt, and you have some spaces without any measurements also over there. So those sensors are not really enough to improve the current forecast. But as I mentioned, there's another data set available in the US, and there things look quite different. So there we have 132 sensors available. Some of those you had to take out because the sensor was a bit old and gave weird data, and some didn't give any data at all, or really small amounts of data. So 111 actually contributed to the study. And as you can see, there's a really densely populated large region, which we can actually work with. And if you now try to assimilate this data set for a month into the icon model, then you see something like this. So this plot is a comparison of 2 forecasts. One with all the weather data inside it, except the en route humidity observations, and one where those observations are actually inside. And the color of those bars is showing you the reduction of the error those model with the extra observations has compared to the other. And the width of those bars is a measure for the significance of this reduction of the error. And the model is compared for different forecast times. So on the left you have 3-hour forecast, then 6, then 9, and so on. And on the y-axis you have the pressure, so the height of where the forecast is. And as I said, we assimilated en route observations. So there on the top, that's where the actual difference in the models comes in. And there you can see an actual significant improvement yielded by those en route observations. So this is seen up to roughly 5 hours of forecast time and gives a really nice signal as well. So this is something which makes our data assimilation people quite happy to see. You would even want to assimilate this data if it would be, well, more or less plus minus 0, because you wouldn't have any data before, but this data is even giving an improvement. So this is something you really want if you want to do a data assimilation. The question now is, okay, this is 111 sensors, which are seemingly enough. Can this number still be reduced? And this is the question we are going to be able to answer, because, well, we can just use less sensors and do the same study again. But that's not done yet. So to summarize, those 111 WVSS2 sensors seem to be enough to improve the ISSR forecast in the US. And we expect that we can reduce the size of the areas we need to give an ISSR warning for. This also seems to show that this well, slightly questionable sensor, but sensor at least, is a quick fix for this problem. And we are going to check if a smaller number also gives similar results, and if similar results would be expected for the EU, where we had not enough sensors. What also needs to be done is to transfer this uncertainty, which is still there, to a measure of accuracy for the ISSR forecast, or for the forecast in general. And that's going to be the next part of this talk, done by my colleague Björn Beckmann.
Björn, are you online?
Yes, I'm here. Could you hear me?
Yes, perfect. You can start. Thank you.
Yes, yeah, okay. Yes, thank you very much. Yeah, ladies and gentlemen, so I'm happy to have been given the opportunity by IATA to continue the presentation of DWD and briefly inform you about ideas for taking meteorological uncertainties into account into the flight planning process. I think the issue of uncertainties was already discussed and yesterday. So then we could come to the next slide, please. Well, I cannot see the slides anymore, but I hope you can see the slides. So please, the next slide, please. The next, please. Yes, thank you very much. Robust decision-making in climate-optimized flying requires uncertainty to be taken into account throughout the entire process. We also heard it yesterday. As a treatment of uncertainties in the context of climate-optimized flying is currently being addressed in various projects, also including in EASA's Aviation Non-CO2 Expert Network, ENSIN, in the task 11, and the meteorological uncertainties within these task 11s are being worked on by the DWD, Meteor France, and the ECMWF. Then further, the LUFO-DECAL project has been initiated a discussion on how to take meteorological uncertainty into account in the flight planning process, which I will be briefly reported on here now. Yes, and please, next chart. Next slide, yes. Currently, the DWD provides a European MRV system and the aviation industry with the data set known as the MET-MRV data set, which contains the various NWP-based meteorological input parameters for climate response models, such as the pi contrails or COSEP and algorithmic climate change functions for the NOx. But however, the meteorological forecast, whether calculated numerically or using AI, will never be perfect, even in the future. Of all the parameters, the relative humidity over ice shows the greatest uncertainty. Therefore, the idea is to quantify the uncertainty of the relative humidity over ice so that it can be described as part of the overall uncertainty in the process. The proposal is to show meteorological uncertainty using a parameter between 0 and 1 and add this to the MET-MRV data set. When used the uncertainty parameter in conjunction with the threshold value, the flight planning tool or flight planning tools could automatically decide on climate-friendly planning. That's the idea. It is considered appropriate to specify the MET uncertainty parameter on a grid point basis for a specific location and time. Yes, and that was also discussed yesterday, but alternatively providing aviation users with the entire set of ensemble forecasts for the MET input parameter so that they can calculate the uncertainty of the climate response is considered, I think, impractical due to the excessive file size of such a data set. So that's why we propose that. Yes, okay, that's a correct slide now. So that means now I would like to show you the distribution of errors for various input parameters based on evaluation of the spread of ensemble forecasts and radiosonde observations. You see here the relative humidity over ice is one of the most uncertain parameters with a large forecast spread. This is shown in the figure. The relative humidity above ice is shown at the top right with a high ensemble spread and high error. Then the air temperature is shown in the middle of the figure, and the air pressure is shown at the bottom left with the smallest ensemble spread and also with the smallest error. However, as I already mentioned, the uncertainty in the MET forecast cannot be completely eliminated by further improvement, also not by incorporating further humidity observations or like that. That will not be possible. Instead, it is necessary to outline an approach for dealing with the uncertainties. Next slide, please. So now I would like to show you a positive example from February last year when quasi-stationary ISSR conditions developed over Spain, Portugal, and France over a longer period of time. In such situations and in such quasi-stationary situations, rerouting will certainly have a climate effect, but that's situations we will not meet every time. So that, please, and the next chart, please. Next slide, please. Yeah. So the probability of ISSR or potential persistent contrail could be as suitable as the MET uncertainty parameter. Why? As the figure shows, the probability based on 10 ensemble forecasts for a 12-hour lead time. The PPC itself is specified as an integer with 0 or 1, and therefore the PPC probability as an uncertainty parameter does not require further climatological normalization. So, and now I would like to present another idea for developing a threshold value. Need this uncertainty parameter together with this threshold, and so now I would like to present the developing of such a threshold value. With the help of a ROC or a receiver operating characteristic curve statistic, a suitable threshold value could be developed based also on this ensemble forecast. The ensemble forecast of the relative humidity over ice is also used here with a lead time of plus 12 hours. were compared with radio sound observations and plotted within this rock curve. What could we see? The ratio of false and true positive rates can be read in this rock curve. A point at the top right of the graph means that at least one of the ensemble members exceeds a humidity value of greater than 100%. The second dot means that at least two of the ensemble members exceed the humidity value of greater than 100%, and so on. And now it takes these three members, or these three ensemble members, this results would be a probability of detection of 0.8 with a false positive rate of about 0.18. So in such POD FPR ratios could be further discussed as a measure of threshold value. So, and I think there are now could be some more questions. So should we use, should every airline then should we use an own threshold value, or should we use maybe one common threshold value within the EU and one common threshold value for the MRV? This could be then further discussed, and is not anymore shown here on these slides. Yes, thank you very much. That would be some first ideas how to incorporate such met uncertainties into flight planning tools. Thank you very much.
Thank you. Are there questions from the room? One question in the back. Over there. Could you just quickly always mention your name and your company or institution? That would be probably helpful.
Hi, Stuart Clark from BALPA. Pilots are used to seeing meteorological forecasts presented in terms of probability anyway, and our flight planning regime is predicated on Prov 30, Prov 40 and other, and interpreting those things. So do we need to really finesse the accuracy of these things? Because after all, if we're trying to avoid making contrails, we can miss the area by a little or a lot. It doesn't really matter. We're just not making contrails. So to what extent do we really need to fine-tune the accuracy of this before we can start to do trials at scale and find out how to run the operation, as well as whether or not the forecasting is working?
Björn, do you want to answer to this?
Yeah, I could try to answer to it. The idea is so that we only consider the flight-optimized flight planning in situation where the MET forecast is has an threshold of accuracy, so that we could only consider these big hits. That's the message, that's the idea behind it, so that we avoid climate-optimized flight routing in situation with inaccuracy MET forecasts.
Okay, we have one question online.
And that we could maybe consider by using this ensemble forecast.
Thanks, Björn. We have a question online. The presence or absence of an ISSR will in part depend on the ice nucleating particle population. To get an ISSR, you need the right dynamics to supply water, plus you need an absence of ice nucleation particles. What do models do about ice nucleating particles? Do they need to do something? Björn, I think that's to you again.
Oh. Ice nucleation, that has nothing to do with this parameter, or? Could you repeat it? Otherwise, it was not really clear for me.
So it's basically saying you need also ice nucleating particle population to form an ISSR, and if models need to work on the ice nucleation particle to really do the ISSR modeling prediction.
Yes, that's correct. That's more a question for our R&D department. So I'm also not really from the NWP department. That's correct. Yes, it's correct. There are possibilities to improve the ISSR forecast by, but if we don't know, but if we have no further information about this ice nucleation, then it will be not possible. But if we could get this kind of information, then it will be also possible also to further improve this cloud ice microphysics and then also the ISSR forecast. Yes.
Thank you. So we will move on to the next talk. Thanks, Björn. Thanks, Marius. It will be presented by Jonathan Itkowitz from the Imperial College London, Observational-Driven Confidence and Contrail Mitigation.
Thank you very much. Okay, next. Cool. So yeah, I'm Jonathan, researcher at Imperial College. I put this together with Vincent Meyer from TU Delft, who unfortunately couldn't be here today due to teaching obligations, but he sends his regards and his sadness he can't be in the room to ask us all very difficult questions. So yeah, I'm going to talk about observationally driven confidence in contrail mitigation. I'm going to break that down into what confidence means in contrail mitigation, how we can actually go about doing that, and then give specific examples of where we're at and where we'd like to be. But first of all, I'd like to thank everyone who came to our conference last September, the Contrail Management Workshop at Imperial, specifically those who came to the breakout rooms for Observation for Science and for Trials, because a lot of the feedback and discussion there is sort of gone into the thinking behind this talk, and we will hopefully see you again this September. So, what do we mean when we talk about confidence in contrail mitigation? I'm going to build a picture about what contrail mitigation could look like in the future, and therefore what we need to have confidence in. So when we're planning a flight or we're executing a flight, we have some flight planning that happens several hours before the flight takes off, and we can have that be contrail aware by integrating things into flight planning software. That candidate routes then go to a dispatcher, and they select their preferred route. They maybe check it, tailor it, standard operating procedures, and produce an operational flight plan. There's then some back and forth between ANSPs and the flight crew during briefing, and you can refine the flight plan. It gets approved, and we get a finalized flight plan, and that's the end of our so-called pre-tactical phase. Then in flight, we can maybe have some tools that are supplied to air traffic controllers or in the electronic flight bag, and this can be our sort of tactical mitigation options, and we can work these all together. Now, I'm being deliberately vague about how this all is exactly implemented, but I'm trying to be very general. After our flights happened, we want to do some post-flight analysis. We want to see what we did and if we did a good job, whatever that means. So the first thing we need is models, right? So in all these different stages, both the pre-tactical and the tactical, we need to supply information to people in order to give them decisions to make. We then want some observations, particularly in our post-flight analysis, to analyze what we did, but we can also maybe chuck in some observations for nowcasting type things during our in-flight tactical phase. And to me, these form two sides of a triangle, with the third step being implementation. So how do we use these models to make decisions and guide procedures around them? And you can see that these three kind of drive each other in an iterative improvement. So we develop models, we make decisions based on them, we then see how we did, and that can drive an evolution forward until we have confidence. And we'll come back to this later in the talk. When we talk about confidence, it's nice to think about what we're aiming for. What would perfection be in this sense? So in our control forecast or our model, we have various components that people have introduced today and yesterday. We have aircraft performance models, numerical weather prediction, contrail formation and evolution models, and some way to estimate the climate effects of the contrails. And at the end of this, we get a prediction for a single flight and its contrail climate effect. Coming from the other angle now of the observations and what we measure, we have a remote sensing source, a way to detect contrails using that and attribute it to this single flight. Hopefully repeat detections of that contrail across its lifetime, and then ways to get a radiative forcing from that single contrail. And in this sort of perfect world, these two numbers are exactly the same, but we know we're not there. So the questions I want to pose and hopefully answer are, what stands in our way from here, and do we actually need to get to this perfect world at all? So last year I was here giving a talk on multi-source observations for contrails. I'm going to draw on some of the things from that, but also people have been speaking about the different observation types in the last couple of days and in the rest of this session as well. So when we're thinking about validation, I like to break it down into validating models and validating trials, because they're slightly different questions we're trying to answer. So for models, the purpose of our validation, the question we're trying to answer, is how accurate is a specific quantitative value that our model is predicting. So we have all of our components, and they all predict key quantities that are important for the contrail evolution and radiative forcing at the end of its life. And we have a whole bunch of validation methods, so it's in situ, IAGOS, chase planes, radiosondes, lab measurements behind engines, and all of our remote sensing options there. And each of them have their own specialty and their own sort of suitability for measuring and evaluating each of these specific quantities. But when it comes to trials, we're trying to answer slightly different questions, right? So it's now, how good were our choices in routing for having a net climate benefit? So instead of being able to quantify all those little pieces, we're asking more general questions, I would say, such as, did we make contrails on our flights? How long did they last? What was their climate effect overall? But now we're faced with a slightly different problem, not just the limitations of the instruments or the limitations of the models, but there's the counterfactual. I think a few people brought it up yesterday. So we can only measure what actually happened. How do we then compare that to what didn't happen? So that can be unmodified route. So what would have happened if we hadn't done new control mitigation, and what would have happened if we had flown as filed versus what we ended up flying. And it's really challenging to do that with just observations. So do we have to rely on models? I would argue no. There are some things we can do. So you can do contextual counterfactuals. So Lauren introduced the Kritos project yesterday, and in Kritos we're using this concept of, we have this specific flight, we fueled with SAF. We want to observe what would have happened if we didn't fuel it with SAF, with just regular Jet A. And so we look for flights that are flying in similar conditions nearby at a similar time that we know have come from a place where we have those fuel measurements. And that's a contextual counterfactual. But we can also perform analysis in aggregate. So instead of looking at this single flight, where we know there are issues and maybe attributing a contrail to that single flight with high confidence, we're more confident in measuring contrails in an area across a space and time. And then we can do this aggregate, more statistical level evaluation, where it's maybe also easier to provide this counterfactual. Now, this sort of speaks to a conundrum at the heart of contrail mitigation, because on the one hand, we have our decision-making process, which does happen flight by flight. You know, the crew, the ATCO, the dispatcher, they want to know the decision they're making on that single flight is correct. But then it's maybe easier or more accurate, more robust to do our validation of our models and our flight trials in this aggregated approach. And confidence sits somewhere in the middle, is like how I like to think about it. So we have our models and our implementation of them and our observation driving iterative improvement until we're confident that those single decisions that we're making on those routes are robust when we measure them and we validate them in aggregate. So that's all fairly nebulous, and I want to get into more specific examples of what we're doing in this space. But before I do, I just want to come back to this, this perfect world, because I hope I've answered now that do we need to get there, or at least I propose my opinion that we don't. But it's still a good thing to aim for. You know, how close can we get to perfection? And so that's what the rest of this talk is about. What stands in our way from doing that, and what can we do to overcome it? How am I doing for time? Okay, cool. So validating contrail models. What we want to achieve is that perfect model, right? We want to be able to predict with 100% accuracy sometime into the future what a flight is going to do. The way we can do that is to use observations to validate specific components of models and iteratively improve them. But there's several issues with that, including technical limitations and observations. So they're often models themselves, thinking about sort of deep learning models for extracting detections from geostationary satellites. But then there's also attributing error, so how to disentangle errors in my humidity from errors in my contrail model. And it's not all doom and gloom, to steal a phrase from Seb. There are resolutions to these problems. So we can improve our observation tools, but that can take a while, it can cost a lot of money. Or we can use multi-source observations. And this is something that was really talked about at the Contrail Analysis Workshop. And that's what I'm going to say on the next slide. So we have seen recently, including Philippe's talk yesterday, we're working on combining ground cameras with geostationary satellites. There's also an example here from the Global Meteor Network that we work with, and we'll hear from Uniwatts and Swiss and SIA in a couple of talks' time about their work in this space. But we also have low Earth orbit satellites. This is from EarthCare, which has some really cool instrumentation for this kind of work. And the phrase that was proposed and talked about in the workshop breakout session was this concept of observation supersites. So these are regions where we have high density of high quality observations at the same time, where we can really start to address those questions of disentangling different model components and also getting over some of the technical limitations of each instrument by itself. So how far along are we in this journey towards perfection? We're starting to investigate limitations of geostationary satellites. So Seb yesterday mentioned Marlene's paper, which is great. And I'll plug my own work, which is upcoming, sort of investigating other aspects of that. We're starting to investigate camera techniques, demonstration of co-location, concepts of this feedback loop between observations and validation. But there's still a lot to do. We need to not just start investigating those limitations, but quantify them and understand them on a qualitative level as well. Bridge the gap, between if I see a contrail in my ground camera and I see it in my geostationary satellite, how do I know they're the same thing? We need to bridge that gap in order to do good validation. And then that breaking down of individual model components. So the final one, if I have a couple of minutes, cool, is how to think about mitigation and confidence in trials. So again, what do we want to achieve? We want to have a perfect model. This time, looking into the past, we can see exactly what that single flight did, and also quantify the difference between that and what we would have done. Now, I've sort of said that it's not feasible right now for all flights, but it is feasible for some flights, sometimes. There are various technical issues to do with sensor limitations and sort of flight matching for observations, and that's that issue of that counterfactual as well. But again, there are resolutions to this. We can change our perspective. We can do that sort of aggregation or validation, measuring our confidence. Or we can do what I've termed here selective validation, where we can perform flight trials in dedicated spaces where we know conditions are good for validation. And this speaks to sort of trial design and not just not doing anything, but when you're thinking about a trial, you should design the trial specifically saying, how can I validate the outcome of this? And that's what I mean by that selective validation. As a quick example of that, we ran a trial in late 2024 with Virgin Atlantic, in collaboration with NOAA as well, where we gave them control forecasts. They tailored flight plans towards that along this Barbados to London route, and then they did contrail management based on that, contrail mitigation. Now, we designed this specifically with validation in mind. So here I'm showing the GOES mesoscale imaging paths that I worked with NOAA to curate for this flight. So each of these images, we have one frame per minute instead of the usual one every 10 minutes. And we followed the flight across the Atlantic there. I'll just play a quick video of what we saw. So you get really high quality observations here. It's flickering a bit because I've not smoothed it out. But you can see that with this, doing this trial with the validation in mind, we're able to get really high quality data. And I'm analyzing this at the minute. So we have done a lot of things. We've got a lot of things left to do. And one of the big ones, I think, and if you come to the breakout session with me and Remy later, hopefully we'll talk about this, is how to do these aggregated observations and how to sort of devise that fairly and attribute that fairly to all the flights in that area and things like that. So that would be me, and I would take any questions.
We have questions online. So one is, do your models allow airlines to assess the extra fuel burn they will need for contrail avoidance routes?
Yes. So,
That's perfect.
yeah. So if you can run through aircraft performance models, you can run the original flight plan, you can run what you actually flew, you can run what would have happened, you can run all of these different scenarios, but obviously having the real fuel data is best. So airlines, share your fuel data, please.
Okay, and then there's just a general comment online on Jet A and Jet A1, which is, I guess, is not only to use to everyone to make sure to use that correctly, because apparently there's a difference between the two. The Jet A is mainly US fuel, and the latter is the rest of the world with lower freeze point and more scope to fly into colder areas. Just a general comment. Then, question here. Do you have the microphone, maybe?
Just to say that I completely agree with you that aggregated validation is the way to go, because we will never be able to do it on a flight-by-flight basis. But I think you can even go further and saying that's the only validation that makes sense, because the climate impact is aggregated. Right? The climate impact is the sum of all those contrails evolving into contrail series. And so I think that's scientifically the only sensible option. Yeah. Of course, it does raise the issue from the airline perspective of attribution and credit, right? How do you divide that big climate outcome into several flights?
Yeah, I really agree in sort of bridging that gap between the single flight and what you can attribute from that big net aggregated effect that we can validate is going to be a super important point for us in the next couple of years, I think.
Unfortunately, we're running out of time, but you can maybe very short. Okay.
You mentioned perfect being 100% avoidance of climate effect of contrails. Should a trial aim for climate impact reductions?
It depends on what you want to do with the trial. So the trial can be investigating specific things like, can we reduce the climate contrail impact by X percentage in a validatable way, or can we change the properties of the contrail in this validatable way? I want to aim to reduce the lifetime. I want to aim to reduce the length of contrail I make. So what you want to do with the trial and how you design it should reflect what you can see and have a specific target for that.
Thank you very much, Jonathan. So we have one last talk in this session, given by 4 people this time. So it's Tanguy Chauvet, Dr. Ben van Leer, Laurent Sauvage, and Maxime Pelassa. Who's going first?
I'm going first.
Good morning, everyone. We're here to talk about validating control predictions again with some ground wide-angle imagers. And this also started at the Contrail Analysis Workshop. So although the one from 2025 was really good, and thanks again for the breakout sessions, the one from 2024 was also good, because there it was organized by contrails.org and Google at that time, and I met Laurent Sauvage there. He was presenting RAeS imagers, and I also met Ben van Leer, that was already using COSIP as a data scientist at Swiss International Airlines. And also with Maxime, my colleague, we have time on our company, which is a consulting company, SII, working mainly for Thales and Airbus. And we had time to talk, to go into the research department of our company and and go into the subject of predictions and observations. So I was convinced I wanted to bring research in the hands of operationals and of industrials. That's why I suggested them that we could do a study about renewable imagers in Toulouse, observing the flights crossing just in cruise, no avoidance, just in cruise above the field of view, and see if the observations are matching the predictions. And that's what Ben is going to start to talk about.
Yes, thanks, Nellie. Yeah, it started with a simple question at Swiss. How much contrails are we actually creating? Let's have a quick look, I thought. And then the question comes up quickly, like, okay, well, how good is this model actually? Like, okay, so it gives us a number, but how many parameters can you change? And how good is this model? And there was not a lot of data. So I thought, okay, well, maybe we need to provide the data, and so get involved in the community. So what do we do in this project? So the workflow is that we look for flights. We just go through all our flights and see if they are in visual range. We have the flight data for this, of course. And then I run the COSIP on this, and then we can see, okay, are they creating contrails in the visual range of the imager? And then I provide the time windows to RAeONIWAT. RAeONIWAT looks for just the visibility, so the filter for cloudiness, because otherwise you don't see the contrail. Then they check if any contrails are present in general, just to see if there's anything visible. And then provide the images to SII, and they will do the final detection of the contrails in a sort of formal manner, and then attribute those contrails to the flights. And this then leads to sort of the main question here. So how often does COSIP actually predict contrail presence correctly or absence? So that's just the main question. But we can go with some more questions then. For example, are the predictions better with full flight data instead of ADS-B? So do you actually need this full flight data, or is just GPS basically enough? So the coordinates. And then do the contrail length, width, and density predictions also seen? So from COSIP as matched to the images. That would be a bit more in-depth question that we stretch goal essentially. So running biocontrols at an airline. So just kind of practical information. You have the choice to do two modes: the grid mode and the trajectory mode. Grid mode is sort of faster, pre-calculated grid values, and you can run your entire fleet on this, and it will be quick. But in this case, we use trajectory mode just to squeeze out the last bit of accuracy in general. So what data goes into the COSIP model? So the engine type for the airplane, of course, the model, and then it's emission index numbers, and also you need to, your wingspan. Well, obviously you know this. Flight data. The bare minimum you need is just the 4D data, so the coordinates and the altitude and the time. And then ideally you also have fuel flow and weight and true airspeed. Then for the last crucial number for me is the engine efficiency, which I rely on the Paul-Schumann model, performance model. But this performance model can also fill in all the other data. As long as you have the 4D data, you can run it. And then the weather data is also important. It is quite large data, so you need to download this. In this case, we use the ERA 5 data set, and it has several parameters that are relevant. And so, then you can run your COSIP on your own and just experiment with it, essentially. So what we do for this project, we start with the full year of 2024 flights, which is way more than 100,000 flights. And so then I filter it for the flights that fly over Toulouse within 30 kilometers of the imager. So that ends up with only 2,400 flights in a year, so you already cut it down a lot. Then we run COSIP on this and to see if, of those flights, how many actually are predicted to have a contrail forming in range of the camera, which in this case was 430. And then there will be another step which we haven't done yet, which is the visibility, right? So are there clouds? Then out of the 430, then it's going to be less than that. So per year you end up with not a lot of data in the end. It's quite rare. Yeah, so lessons learned is my last slide, and then I hand it over. So sharing data is quite difficult, just for privacy reasons and the unions involved. This can take quite a long time, so you have a bit of lead time there. Yeah, of course, but you can the flight windows you can use, of course, because they're publicly available. So maybe you don't have the capability to run COSIP on every flight. Might be limited because you need some programmers for this. Yeah, and also a question is it actually even worth it to do this within the airline? Because you don't know, you have the publicly available data. And what would be nice as a sort of wish is that there's more standardized COSIP code. So at PyContrails, the tutorials are pretty good already, but it would be nice if that's more of a set manner. Yeah, so of course the ground operations, the ground observations are complex. So this you probably cannot do inside your airline, and I gladly hand this over to Bellouin.
Hi, everyone. Thank you, Ben and Tanguy, to give me the opportunity to work with you on this campaign and to the organizer and Nellie for this very neat organization and room. It's very nice. So briefly, I will give you provide you with some insight on the SkyMager capabilities, and first of all, to think about what we need in terms of observation from a remote sensing point of view. Very briefly, because it has already been discussed by other presenters. So you need to follow to see the Contrail life cycle, observe it from the beginning to the end. And satellites, they make a terrific job to observe the major development, but they miss what we call the appearance lag. So the first minutes of life, and it's where the ground SkyMager they can work and make the job to grab the inception and provide information to be able to make the attribution with flights, and then follow the contrail until they can match with the satellite information. So how we can get, depending on the needs, you can use different type of sensors. So if you want just to detect the formation, you may use only partial field of view, or what you call narrow field of view visible cam, or enhanced visible cam that's been successfully used by Eurocontrol, MUAC, or MGN to make some attribution. But if you're going to go a step further and to track the contrail on a more mature way for day and night, then you may need wide angle, because you can follow from one horizon to the other until sometime to 2 hours. You can use wide angle visible or enhanced visible imagers. And if you're going to go on the next step, which is relative information that you may need as well for validation or constraint of the model, then you need to use, or you can use the long wave infrared wide angle imager that will provide you with some optical depth of the contrail. So with the wide angle, you can, if you take a typical contrail at 10 kilometer high, you can monitor a surface of around 30 kilometers radius or more, but we limit this to 30 kilometers because we don't want to go too low in elevation. So it's like it's higher, it's bigger than the Great London, for example. So, and you see that you can, with one single camera, you can see a different type of contrail at the same time and follow it on a long period. So at RAeNIWAT we provide both kind of system, visible high resolution system. It's like a few meter resolution, and so it's very high result, but there are some saturation effects sometimes. So there are some limitations with this system, as anyone. And we provide also the thermal imager, which is day and night monitoring, and we can retrieve for the cloud optical depths with a good accuracy. And so it's industrial product with low maintenance, it's easy to deploy. And with the hardware, we provide also an automatic way of providing new different type of features, and we improved this during the campaign, so thanks to Swiss. You need a very accurate geometrical calibration to be sure that you know where you locate the contrail on other objects. And you need also to have automatic obstacle detection, rain, human, insects, or this type of contrail with, like, for example, like lizard. So you want a clean database to erase all this. And then you go to the cloud cover detection, so structure, you can follow it, and at the end, you provide the optical information. So all this every 30 seconds. So for the Swiss experiment, we used one of our systems in Toulouse, which is well located on a trajectory, like a kind of entrance or out, exit door from the south of France for northern trajectory to the southwest. And but we have other stations of the same type over Europe, where it's on purpose. But I found that they were quite nicely located underneath some major tracks with warming effects. So they are available. And I think this SEI has done some work with our system. So take away. I've already said that, but so it's industrial. It's available, and with it's better to use wide angle if you want to follow the evolution of the contrail. And with the thermal imager, you can go a step further by providing some relative information. Thank you.
It's not finished. And just, I'm going to be quick, but just to say that then the last part is on SII to have these 3 steps where we have the images, we consider the calibration of each cameras, we also sort of, if we've got visible or thermal infrared images, and then we annotate, we label manually, and then we also launch some trained computer vision model, but what you're going to see is mainly manual. And after, we also run COSIP, but on our own, so just to compare with what Ben did on the Swiss side. We try to have the same parameter, but also we try to have different aircraft model, performance model, but Era 5 reanalyzes. And then we put everything on the same map to attribute what has been predicted and to see what has been observed on such kind of map here. But then also we wanted to create, before that, we ended up with a few flights where the good conditions were there to be able to observe it and also to conclude into these things. So, for example, for this 4 flights, we see that the predictions was agreeing with what we observed, for example, with absence of contrails for the first flight, or with presence of contrail for the 2 last one. And now we are going to extend it to more flights. We provided an interface to be able to show that, but not by saturating the interface with too much things. So we separate, you're going to see that after with my colleague, for the dataset of Swiss. But also what you saw with Philippe Véry yesterday, the GVCCS, he asked us to show that on the interface here. And also Thales with the Decor project, making some contrail avoidance with Amelia Airlines, asked us also to have at one point verification of the absence of contrail while doing some avoidance, vertical avoidance. And now you're going to see what will be presented by my colleague.
Hello. So now I can show a bit of our visualization tool called the Contrail Tracker. So here we are at the homepage of the interface. So we are all above Europe. And here in the top left, we can select some cases that we have studied that correspond to some observation slots we had. So several cases from Eurocontrol GVCCS dataset, for example, or Thales and Amelia experiments that Tanguy just mentioned, or of course the 4 first Swiss cases that we studied also with Réuniwatt. So for example, if I pick 8th of April, we go toward Toulouse where we have the Réuniwatt camera, and we can slide here and see the Swiss flight that we have targeted for this case. going through the field of view of the camera. And when I click on the camera, I can check the images that have been taken by the Renewat imager. And here one can guess the contrail here is produced by the Swiss flight. And this is what we could attribute by doing the analysis work that Tanguy also mentioned. And so we could effectively attribute this contrail to the Swiss flight here. And finally, we can check the COSIP prediction. So when I click here, I get the COSIP prediction we made on this flight. And we can here see that there is an agreement between the what we have observed and attributed to this flight and what is predicted for this flight. Then I can select another case to, for example, on the Eurocontrol camera. So we jump to Bretigny where the Eurocontrol has installed the camera. And so here we can see that all the flights have been retrieved and are also attributed. And we can go through all the observation slots and make a much more comprehensive comparison between observation and predictions. And for instance, here, around here, there is a Swiss flight that we can also check if we want. And in this case, there is no prediction for this flight, and there is no detection as well. So it's another agreement between observation and prediction, even though there are none, actually. And so one goal is to aggregate all the statistics of comparison between prediction and observation. So here it's still under development, and numbers are not to be taken for granted because there are still a lot of uncertainties. Some of them, we signal them with a gray color, with, for example, the dark gray and the light gray. So dark gray are cases where there is no prediction and no observation. And the light gray is when there is a prediction from the model but no observation. So in both of those gray cases, there is no observation, and it's still uncertain because when there is no observation, we cannot be 100% sure that what we were looking for was observable or not. Like, it doesn't mean it doesn't exist. And cases where we are a bit more sure are when we actually found something in the image attributed to a flight, and then we check if it has a prediction corresponding, it's a green case, and if it has not, it's a red case. So one goal is to aggregate statistics like this, and eventually also to compare different setups of predictions. Here we can compare when using a BADA aircraft performance model or Paul Schumann, and then also check if there are some correlations with respect to altitude. Here we can see a vertical view where those are all the altitudes of the flight going through in this case. And one goal would be to study if there are some correlations between when prediction and observation agree and the altitudes of the flights, or eventually also the aircraft type. And yeah, as I mentioned, we can also aggregate the statistics on all the cases we have imported in our visualization tool. So if I click here, and yeah, one goal would be to have more variable statistics to understand what's happening with prediction models. And of course, we could imagine like filtering for a specific company, for example. And this is what we will try to do by expanding our analysis with Swiss from 4 flights to hopefully, several hundreds.
Okay. So currently we have up to 500 Swiss flights. The images for, or will be soon. What we can do with this is, of course, the analysis that we just talked about, and that will give us hopefully a good idea about how the COSIP prediction actually works. That's it for us. That was a nice demo from Maxime. Thank you very much.